Today I'm going to talk about vectors. When we talk about a vector in physics, we're just talking about something that can be displayed as an arrow or thought of as an arrow. So when you say the word vector, probably the first thing you just want to start with thinking in your mind is arrow. And to draw an arrow, you need to know how long it needs to be, and you need to know what direction to point it in. And when we talk about defining vectors, that's all we're doing. We're writing down a specific way that clearly states how long it is and which direction it is. So if I draw an arrow on my paper, just to reiterate that, I need to know how long to draw it. So let's say I need to draw it 2 centimeters long. And then I need to know what direction to draw it in. And that direction can be given to me either as an angle that I'm referencing off a specific line. For example, if I want to think of horizontal and vertical, I could know the horizontal direction, the horizontal line, and I could measure the angle that I drew my 2 centimeter long vector off of that. It would matter which direction I went away from my horizontal direction here to reach the vector. If I went counterclockwise, that's the angle I just drew in there, that would be one angle. But I could have gone and measured this angle clockwise, which would have given me a much larger angle. So how I define my angle is really important, and so that we all understand which angle we're talking about, we have an agreed upon angle ahead of time that we all agree this is the angle we're talking about when we talk about the polar angle. The polar angle is always defined the same way, so that no matter who you're talking to, you don't have to redefine it every time. You say, oh, it was the angle measured blah, blah, blah. It was the angle measured this way. It was the angle measured that way. Every time you tell somebody angle, you don't want to take the time to explain how you measured that angle. If we all know ahead of time how this angle is always measured, then we don't have to spend the time doing that. So the polar angle is always measured off the positive x-axis, so it's the horizontal axis. If we have a vertical axis here being our y-axis, and then the horizontal axis would continue off in the negative direction, and the vertical axis would continue off in the negative direction as well. The one we're measuring it off of is this horizontal positive direction. We go from that axis up to where the vector is in space, and that is the polar angle. So that's really important to memorize. You just need to know that. The other thing you needed was the direction. Once I knew, not the direction, the length of this arrow, once I knew the length and this polar angle, I can draw this vector when asked to. And I'll label this vector A. Capital A is now the variable label for this particular vector, and I know it's a vector because I used this little symbol on top that's either a full arrowhead or, like a lot of people just do a shortcut half arrowhead like that. They mean the same thing. It's just stating that this is a vector, so it has both a length and a direction associated with it, not one or the other, but both of them to fully describe it. If I want to take this vector and write it not in terms of its length and angle, but instead write it in terms of something else, I would have the option of doing the Cartesian notation. Cartesian is like x and y components for my vector. So my vector A, wherever my vector A is, when I draw it, looks like that. I can think of getting from the tail of my vector to the head of my vector by moving a certain distance in the x or horizontal direction, and then moving a certain distance in the vertical direction. which would be the y direction. Whether that motion was positive or negative is important. What I've drawn here is in the horizontal direction to get from the tail to the head of vector A, I moved in the positive x direction. So I know this value would be positive. If I had moved in the negative x direction, I would be going leftward, and the arrow tip would have been over on this side of my reference frame here. So it would have to have been in the second or third quadrant if my x was negative. And same thing for the y. As I move from the tail to the head of the vector, the direction I took in the vertical direction to get there matters. I went up in this reference frame, which would have been I moved positively in this reference frame, and so AY is positive. If I had moved down to get to the tip, the head of the vector, then it would have been negative. So let me show you a vector that's not in the first quadrant. If my vector is here, vector A is that vector instead, then to get from the tail to the head, I'm going to move in the positive horizontal or x direction, and I would move in the negative vertical direction. How long do I know to draw? How do I know how long to draw this horizontal vector or component to A? I go from the tail until I reach the point where the head of the vector is perpendicular from that x direction, straight out perpendicular from it. All right. Now, let's take one of these vectors, and we'll just do one real quick in the positive, positive. So it's going to be in the first quadrant. It's a positive. Let's call this one B. And let's say B has a length of 3 meters in length. And to write the length, I put the lines around B. That's its magnitude. And it's going to have a y and an x component, like that, bx and by. And let's see if we can figure out, calculate what bx and by are using just the length of the vector and the angle. Let's say this is 55 degrees. There, that angle. And that would be the polar angle because it's measured off the positive axis, the positive x-axis, in the counterclockwise direction until we reached vector B. Okay, so if I want to calculate the x component of this, I'm going to think of my vector as a right triangle. And when you're working in Cartesian or the xy components, you can always think of it as a right triangle. So this is just a triangle then. B is my hypotenuse. Bx and by are the sides. And I'm just going to write there, just everything's going to be positive here. And then this is 55 degrees. So this is 3 meters. So if I'm looking at my right triangle, then what I want to do, let me see if I can get this more in focus just a little bit. Maybe there. Is use my sine, cosine, and tangent functions to work between angles, hypotenuses, and sides. So if I want to solve for this side right here, the x component, then I'm going to take my triangle and I'm going to use the angle and the length And I'm going to solve for this side here being a positive value. And this side I don't need to think about right now. I'm just interested in this side. This side in this triangle with this angle being the angle I know is the adjacent side to the angle I know. And that's important because that's going to tell me which of my functions I want to use to solve for that side. Because it's adjacent, I'm going to use cosine. Cosine of the angle is equal to the adjacent side over the hypotenuse. This allows me to solve both sides multiplied by 3 meters to give me the adjacent side length. It's just the length of it. It's not positive or negative, it's just always positive. 3 meters cosine of 55 degrees. So I just need to do that calculation, and that will tell me what my side length is. It's really important to make sure your calculator, if I'm plugging in 55 for my angle, then I need to make sure that my calculator is set to degrees. And every calculator is different. It'll be under the mode or something like that, settings, and you can do your degree or radian. Sometimes there's a button that just switches back and forth, or swaps back and forth between the two. So 3 times cosine of 55 degrees is 1.7. And that'll be meters. All right. So now I have that x component. That will allow me to write my vector b, or get started writing my vector b as a vector in Cartesian. I want to write b equals whatever the x component is, and you would have a real positive or negativeness to this, x hat or I hat, depending on which system you're using, plus by y hat or j hat, again, depending on which system you're using. And now I know to plug in 1.7. Now I got to go back up to here because everything I plugged in here was just using a positive. It's just all lengths. I'm just using lengths and thinking of this as just a triangle. But in reality, we're representing a vector which has directionality to it. So because I moved in the positive x direction and the positive y direction to get from the tail to the head of this vector, I know that bx and by are both going to be positive. So I can just go ahead and plug in the positive value here, and that's okay. 1.7 meters x hat plus, I need to plug in something, y hat. I need my y component. That's the side of the triangle that is parallel to the y direction here. So that means I'm solving for this side here now. I'll just redraw this again so that it's not so cluttered. It was 3 meters. It was 55 degrees. And I'm interested in this one over here, which is just by as a positive value. Because it's opposite, the side I want to solve for is opposite the angle I know, I'm going to be using sine. I use sine because sine of theta, which is 55 degrees, sine of the angle is opposite, which would be by, over hypotenuse. I solve for the opposite side by multiplying both sides by 3 meters, which was the hypotenuse, and that gives me by magnitude as this calculation, 3 meters times sine of 55 degrees. So I just plug that into my calculator. Again, making sure that my calculator is in degrees. And I get that the length of that side, the opposite side, is 2.45 such and such, 2.5 then meters. Now I have a number to plug in here in my y component. And again, I know it's positive. because of the direction I had to move in the y direction within my reference frame here was up, so it was positive. So go back here, just rewrite my b vector by plugging it in to that y component. B equals 1.7 meters x hat plus, now I can add the y component, 2.5 meters y hat. And I've taken a vector that was in Cartesian, within polar, there we go, as length and direction, and converted it into Cartesian with an x and a y component, which is really just the length of the two sides of this right triangle, where one side is parallel to the x direction and the other side is parallel to the y direction. Now, if I had a vector in polar that was not in that first quadrant, but instead, say, right over here, in that quadrant, call this vector C, and let's say C is, well, let's say it's 3 meters in length, just like the B, and let's say the angle is 55 degrees here. So the polar angle would be 180 plus 55, because the polar angle would be all the way around from the positive x-axis. So that would be 180 degrees plus 55 degrees. That's my actual polar angle for this vector, which would be equal to 135 degrees. But the angle that my new vector makes with just this negative x-axis is 55 still. So the side lengths as positive values will be the same here. We still have, if we redraw our triangle the way I did previously, it's going to be 3 meters. It's going to be 55. And then, let me draw it bigger so you can see that better. It's going to be 3 meters. This will be 55 degrees. And then when I do the x component, it's parallel to the x-axis. It's this one. It's going to be cx and some positive value, and cy and some positive value. But if I look back at the vector itself, the components for this vector, if I think of the sign of those, are they positive or negative? To get from the tail to the head, I moved in the x direction negatively, and then I moved in the y direction negatively, so that my components should be negative, negative. Negative x hat, negative y hat. All right, so when I come back here, if I want to solve for the adjacent side to the angle I know, that's going to be using cosine. I'll still have 3 meters cosine of 55 degrees gives me that adjacent side, which in this case is my x component. So I'll still have the same x component I had previously, which was 1.7, which I calculated here using my cosine times the hypotenuse 1.7. So it's still going to be 1.7. And if I'm just thinking of the length of it, it will still be positive. But now when I write my vector C, it's going to be in the negative x hat direction. So I need to put that negative back in, x hat, because I know that when I moved in that direction, I went in the negative direction. And then I'll have the same value for my y as well in terms of its length, 2.5 meters. And again, I moved in the negative direction. So that's going to be negative y hat. And there's my vector C. in Cartesian. If I had Cartesian and I was meaning to go to polar, I would use the idea that my triangle looks like this, and I would use, I wouldn't know that, the magnitude of C would be the hypotenuse, and I have just these two sides, 1.7 meters, negative 2.5 meters as the directions, and then my C was like that. So you can just think of this as a triangle again, with C, length, and just make these positive. It's just a triangle, so they wouldn't be a negative, just side lengths then. And you just think, okay, well, if I want the hypotenuse knowing the two sides, I'm just going to use Pythagorean theorem, so that C squared equals the sides squared added to each other. Then you take the square root, so it's the square root of the two sides squared and added to each other. So the x component plus the y component, and then add it together. And if I do this calculation, as long as there isn't too much rounding in my previous calculations, I should get a value that is close to what I know the length was, which was 3. And I do. So if I do this calculation on my calculator, I get 3.0 meters. Is the length of my vector C. So I have part of my polar vector now. And you don't have to worry about this one. You can just plug it in and solve always using Pythagorean theorem. The thing you have to be a little careful with when you're going from polar to Cartesian is to get the signs of these directions correct in your x and y components, because if I know that my vector is this vector here, which I drew in vector form here, I know that I went negative in the x and negative in the y. So all I need to do is realize that I'm over here in this quadrant, the third quadrant. I need to get the angle here that's made, and then from there I would add the 180 to get my polar angle. So let's just do that. So we're going back from Cartesian with this exact same vector to polar, and that means we really only know the side lengths. So if I have the side lengths, and I know which direction they went, so I do know which quadrant it's in. It was negative 1.7, like x hat, that one. Negative 2.5, y hat, it's that one, that. All right, so I know I went like this into the third quadrant. I need this angle here, which I'm going to call phi, and that angle is not my polar angle. Once I get this angle, I can use it to calculate the polar angle. It's only the polar angle when my vector's in the first quadrant. So right now it's over here, and if I were to put this vector into like an axis reference frame, you would see that the polar angle comes from the positive x-axis all the way around the vector. So that the polar angle theta equals 180, the straight line, plus the little angle phi. So I calculate phi by using my tangent. Tangent, what I know is opposite and adjacent sides to the angle I'm interested in calculating. The tangent of phi equals opposite. And I'm just going to put in positive numbers here. This is what I always do so that I don't think that my calculator is going to magically stick me in the right quadrant necessarily. So what I'm really doing is, again, transferring it all back to just being a triangle. I'm looking for this angle right here, that angle, and I have 1.7 meters and 2.5 meters, just as triangle side lengths. Okay, so my angle I'm interested in solving for is this one. Opposite is the 2.5. Adjacent is the 1.47. Opposite, so literally you go straight across. That's that side. Adjacent means it's touching the angle. If the side you're talking about is actually touching what you draw in as an angle, then that is your adjacent. All right, so to solve for phi here, I need to take the inverse tangent of both sides. That will give me phi, because it inverts my tangent. And then I just have the inverse tangent of 2.5 meters over 1.7 meters. And I get, when I take tangent inverse on my calculator, 2.5 divided by 1.7, I have 55.7, so I get 56 degrees, and this is a rounding issue. I would have needed to keep more sig figs here to make sure that I got the exact same angle out that I had created those with. That's why it's slightly off, but the method's fine. So as you're going through, you're just really working with your vectors as triangles. When you talk about a vector, you immediately think right triangle. The sides are the components of the vector. The hypotenuse is the vector itself. The length of the vector is the hypotenuse. And then the angles are what's giving you like that polar angle. So once I have my phi, I can get theta is 180 plus that value. This would be my true polar angle. And then I have C. C is 3 meters and then 136 degrees. There. Okay, so practice your right triangles a lot. Work on going one way and the other way in mini quadrants. Just make a vector in one of the quadrants and decide on a length and angle for that vector and find the components. Make sure the components make sense. Are they positive or negative as they should be? Then go from components, draw a vector in whatever quadrant you want. Try to use different quadrants. You've like done all the different quadrants, and take it from those components back to polar, so that you're getting the angle and the length. Make sure that when you get the angle, that you're really getting that polar angle. So if it's in a quadrant that's not the first quadrant, the angle is, you're going to have to do something to the angle to get the polar angle. And it's good practice. Just go back and forth. Use book examples if you need to. But definitely practice until it starts to become second nature. You're okay with it. You feel comfortable with it. All right. See you next time.